Hello everyone, my name is Nick. I'm with VoltForge Labs, and today we're going to be talking about the science, production, and real-world potential of PHA. Its full name is Polyhydroxyalkanoate. I'm going to say it one time at the beginning of this video, and I am not going to say it again. So, what is PHA? PHA is a biodegradable polymer. What does this mean? It means that if you throw it away into the environment, it will degrade into water, carbon dioxide without leaving behind bad chemicals or microplastics. So, it's a polymer produced by bacteria that biodegrades naturally in the environment. It's an eco-friendly alternative to the current plastics, which would be petroleum-based. And it has an extremely high polymer count, which makes it extremely versatile because each of these polymers has different attributes that can be utilized in industry. So, with over 160 polymers, PHA is extremely versatile. It has short chain length polymers, which you can see is C4 and C5 at the bottom of this infograph. It has medium chain length polymers, which you can see as C6 through C12 on this infograph. And there are long chain length polymers, but I'm going to omit them from this video just because they're not very commercially relevant. Alright, so for the short chain length polymers, you can see in the blue we have P3HB, C4, and in the green we have P3HHX, which is C6. C4 and C6 correspond to C4 and C6 on the previous slide. So for C4 we have the most common and well-studied PHA. It's highly crystalline, it's stiff, and it's similar to polypropylene. This can be used for medical implants, drug delivery, packaging, but it has limitations. It is brittle on its own, and it's often copolymerized to improve its toughness. This is true for a lot of PHAs. They can be copolymerized, and what that does is it takes two different types of PHA and it mixes them together to add their strengths and reduce their weaknesses. So as you can see for C6, this one is often copolymerized with P3HB, which was C4, to reduce brittleness, flexible, and it's biocompatible. This one is used for tissue engineering and scaffolding, sutures and surgical meshes, controlled drug release, and cardiovascular devices. So if you look at C4, the second, drug delivery, slow release capsules, and microspheres, I'm really excited to see where this specific medical portion of PHA can take off. If you don't know what a microsphere is, it's a small plastic sphere that has medicine put inside of it, and it can be injected into the body. And once it's injected into the body, it circulates, and it can either release over time. It can be heat release, so when it reaches a certain temperature, it'll release the drug that's held inside of it. It can do when it comes in contact with water. If it reaches a certain acidity, it'll dissolve. But it's really exciting to think about what a biocompatible and biodegradable plastic could do for this specific portion of the medical industry, especially one that doesn't leave behind microplastics. All right, and then moving on to the medium chain length polymers, we have C8, C9, C10, C11, and C12. So starting with C8, we have P3HO. This is one of the most elastomeric PHAs. It's rubbery and tough. It would be used for latex-like applications, cardiovascular patches, piezoelectric materials, and bioprinting inks. Moving to the middle, we have C9 and C10, which are P3HN and P3HD respectively. These are longer chains, they're even more flexible, and they're hydrophobic. These would be used for cosmetics and personal care, coatings and adhesives, and marine applications. And then moving to the far right, we have C11 and C12, which again are P3HUD and P3HDD respectively. These are very long, very waxy, and highly hydrophobic chains. These would be used for things like wax replacements, gene delivery vectors, and specialty lubricants. So, comparison with conventional plastics. Unlike conventional plastics, PHA is a renewable resource origin. What does that mean? It means PHA is made from renewable resources, unlike conventional plastics, which come from fossil fuels. If you don't know, the majority of plastics that you see in your day-to-day life are petroleum-based. That means they come from oil. So, another comparison is PHA's natural degradation. It's able to biodegrade in the environment, unlike petroleum-based plastics. This reduces plastic pollution compared to conventional plastics. And because PHA has a circular ecosystem where it's made from bacteria and it can be biodegraded by bacteria, it has an extremely low environmental impact, and it reduces dependency on non-renewable materials. All right, so moving on, we know some things about PHA now, but how is it made? All right, well, it's made in these fermentation tanks. So there's really two steps that go into PHA production. There is a growth phase and a accumulation phase, and we will kind of get into that a bit more. But during the growth phase, there are different feedstocks that you would feed PHA. They would include sugars, plant oils, and agricultural waste. The feedstock you choose can impact the yield and cost to produce the PHA. And the most common feedstocks currently being used in the market would be sucrose and glucose. Those can be gotten from sugarcane, cornstarch. These are utilized because they result in high yields and they're well understood. There are also experimental feedstocks that are being looked into, things like waste cooking and vegetable oils, dairy waste, whey protein, and others. So, PHA is the energy carbon storage reserve for the bacteria. In a normal cell that's not in a lab environment or not disturbed by humans, PHA could account for 1 to 10% of the dry cell weight by volume. However, when you deprive a cell of nitrogen, phosphorus, or oxygen, it will start mass producing PHA due to that stress. So the excess carbon gets diverted to the PHA synthesis instead of to cell growth. And in situations like this, PHA can accumulate rapidly, and the resulting effect can be it accounting for 80 to 90% of the dry cell weight. And circling back to what I said, this is achieved in industry through a two-stage process. You have a growth phase followed by a deliberate nutrient starvation phase, and this triggers the maximum PHA accumulation within the bacterial colony that you're growing. Once you have the colony of bacteria that is full of PHA, you have to remove that PHA from the colony. There are a few ways to do this. The two we're going to talk about is solvent and mechanical. The first one, solvent, would be using chemicals to dissolve the cellular material around the cell, leaving only the PHA behind. The mechanical disruption method is exactly what it sounds like it is. You break apart the bacterial cells physically to release the PHA. This would allow you to avoid using harsh chemicals. Now, for next-gen PHA, which is being worked on right now, it would be cell-free fermentation, where you would bypass the bacteria, and instead of using bacteria to make the PHA, you're just taking that carbon-rich plant matter and using a chemical process, you're converting that directly into PHA. That's going to do a couple things, right? That's going to reduce the cost, and it's going to increase the output, both of which are very important if you want to compete with oil-based plastics. And each of these methods have environmental considerations, but I think they're far better for the environment than petroleum-based plastics. Moving on, we have challenges in scaling PHA production. PHA needs to be able to compete at scale with other plastics if it's going to be cost effective for consumers. So a couple of those challenges are high production costs, process optimization. There just isn't as optimized of a process to take these raw materials and get to the output as there is with other plastic manufacturing processes. A solution to this would be more engineers, more attention, more money, right? These are all things that the plastic industry has had for decades, and it's things that PHA is going to need if it wants to compete. You need more engineers working on solutions. You need more money to fund those engineers, to fund research. And you just need the general population to be aware that, hey, PHA is a thing, and I have an option to utilize it if I so choose. And then one that's not so critical but still worth mentioning would be feedstock availability. You need the feedstock to feed the bacteria to convert to PHA, and without feedstock there is no PHA. So feedstock availability, that would affect scaling production of PHA. All right, moving on, decomposition and environmental impact. So, PHA can biodegrade in soil, in marine environments, and in compost environments, and it biodegrades naturally. It leaves behind no microplastics and no harmful materials. So PHA plastics degrade in soil through microbial activity, converting polymers into harmless water and carbon dioxide. PHA plastics naturally decompose in marine environments without leaving harmful residues, preserving aquatic ecosystems, and composting conditions accelerate microbial degradation of PHA plastics, turning them into water and carbon dioxide. There are factors that either stimulate the decomposition rates or reduce the decomposition rates, and they're pretty straightforward. They're arguably the same factors that would increase microbial life: temperature, moisture, the presence of microbes, and the composition of the PHA. So higher temperatures usually would mean more microbial activity. That would increase the decomposition rate. More moisture would mean more microbial activity, and that would increase the decomposition rate. And the presence of microbes obviously would increase the decomposition rate. Now, one thing to consider is, because there are so many polymers of PHA, some may biodegrade faster than others, so that is also something that needs to be taken into consideration and researched on a case-by-case basis. All right, so we have lifestyle assessment and sustainability. Environmental impact comparison. So compared to traditional plastics, PHA would have reduced greenhouse gas emissions and a much more sustainable sourcing and disposal. One thing to note is that traditional plastics don't really have a sustainable sourcing or disposal methodology. They're usually single use. We have recycling in America. It's not great. I think it's like double digits, like less than 20% of all the plastic gets recycled, and it doesn't biodegrade, so it just sits for hundreds of years non-degraded. Because PHA is a circular ecosystem where it's made from plastic and it can be consumed, or not made from plastic, made from bacteria and consumed by bacteria, it's extremely sustainable and its disposal is extremely easy. Even if we kept the same recycling system with PHA, the 80% that doesn't make it through recycling would still be able to degrade naturally in the environment, leaving behind no damaging chemicals. All right, so practical uses and applications of PHA. We have biodegradable packaging, disposable cutlery and bags, and reducing plastic waste. So PHA is used to create biodegradable packaging that decomposes naturally, reducing environmental impact. It can be used to make disposable cutlery and bags and offer sustainable alternatives to traditional one-time use plastic items. And this would help reduce plastic pollution in landfills and oceans, promoting a cleaner environment. One thing that I'm super interested in with PHA is 3D printing filament. Sitting next to me on my desk while I make this video, I have a yellow roll of Ecogenesis PHA and a red roll of, I believe it's Polar Filament PHA. And I'll probably leave links to them or their YouTube channels if they have them in the description of this video. But that's something I'm super interested in, to see how PHA compares to like PLA or PETG if you're into the 3D printing community. And I'm going to be releasing a video on that later anyway. So more uses for PHA would be medical and pharmaceutical uses, right? We've gone over these. You've got medical devices and sutures, drug delivery systems, tissue engineering applications. Industrial and agricultural applications for PHA would be PHA in mulch films, controlled release fertilizers. I don't know if you've ever looked at like a bag of mulch, but you have these little brown spheres that if you squeeze them, they pop. That's a little fertilizer. Those could be made out of PHA. You have sustainability benefits, right? It promotes sustainability by enabling natural degradation and reducing environmental impact on the farms where we grow our food. So, a few things about PHA in conclusion. It's a biodegradable alternative to petroleum-based plastics. It's eco-friendly. and it's overall just better for the environment and better for humanity. Sustainable production. It's produced through sustainable methods that minimize the environmental impact and support green manufacturing. Versatile applications. Because of all of its polymers, it can be used for just about everything. If you want to get something done, there's a PHA polymer that'll get it done for you. And innovation and scaling are huge tackles for PHA, but not just that, just the information on it. I scoured YouTube and I just could not find very informative or well laid out information on PHA. And it just it needs to be more well known, more well researched, more money needs to go into it. So again, if you want to check out Polar Filaments PHA or Ecogenesis, they helped me a little bit with this video, and they're great companies. You should give them at least a search on Google. But that's it. I hope you liked this video. I hope you found it informative. I'm going to have 2 more videos about PHA coming out. One's going to be for 3D printing. It's going to be comparing PLA, PETG, and PHA for prints. And then I'm also doing a degradation test on PHA, where I am testing PHA in dirt, water, and a compost-like environment to confirm the claims that it does biodegrade and it does leave behind no waste chemicals, no microplastics, anything like that. That video is more likely to take a year to come out, but keep an eye out for those videos. And again, I hope you like this, and thank you for watching.